Okay, so is my slide visible to all of you guys? Am I audible? Hello? Is my slide visible to all of you guys?
Yeah,
Yes, sir.
yes. Yes,
Okay.
please.
Okay, so a very good evening to the week 3 discussion of this course, Introduction to Machine Learning. And this course is originally taken by Professor Balaraman Ravindran, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras. Okay, and my duties for this course is I am a PMRF TA for this course. My duty is to solve question that are very similar to your assignment, so that whenever you will be doing your assignment, you will not feel it is a totally new thing. Okay, but before going directly into the question, what I do is I also cover some of the yeah.
Sir, your voice is echoing, please.
Is it echoing?
Sir, we are getting feedback, sir. Your voice is.
Okay, now is it clear?
Yeah, now it's
Okay.
Yes, sir.
Yeah. So yeah. So I was telling that before going directly into the question, first we will discuss some of the theory related part that I feel it is very essential for all of you guys, at least to know the concept of this. Okay, you have seen in your lectures that it is a very mathematical part, but it is always good to know the little bit of theory or concept behind that. That will also help you, so that I will cover, and then we will discuss some of the questions. Okay, so last week what we have discussed is linear regression. Okay, some of you are still joining. So last week what we have discussed is linear regression. Okay, what we have discussed linear regression, uh, how to form the equation of the linear regression, then how to fit the linear regression curve to the data that we do by RSS, that is residual sum of squares. Then if we differentiate the residual sum of squares with respect to coefficient, then we can get the best coefficient. Okay, we can do that by putting the residual sum of squares RSS with respect to your coefficient equals to differentiating the RSS with respect to coefficient and equating it with 0, so that our RSS will be minimum. Okay, But today what we will see, also we have discussed regarding the problem of dimensionality. Okay, we okay. Yeah, we solved the problem of this dimensionality with two things. One was feature selection, other was feature extraction. Feature selection, we have seen subset selection, and feature extraction. We have seen principal component analysis. Uh, 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 Apart from this two, also in the middle we have seen a thing called shrinkage methods. Okay, such that we shrink our coefficient very close to zero. That coefficient, that input variable that is not important, we shrink that with respect we shrink that very close to zero. We do that by two methods. One was lasso, and other was ridge regression. Okay, lasso, ridge regression is your L2 regression, L2 regularization, and lasso is your L1 regularization. Today we will see about linear classification. Okay, linear regression was over last week. Now today we will see a bit about linear classification. So what is this linear classification? Linear classification, it refers to the categorizing a set of data points into discrete classes or groups based on linear combination of its explanatory variable. Okay, so this is the definition. We will see with the help of curve. Last time we have seen linear regression. Okay, linear regression means we have data point, we have fitted a line to it. Okay, that was linear regression. But today we will discuss about linear classification. What is the difference? Linear classification, we are interested in categorizing our data points in more than one feature or more than one groups. Okay, so how we can do that? We can do that by putting a simple straight line uh, in between our two data groups. Okay, so you can see here there are two data groups, one denoted by red points and one denoted by blue points. If we separate these two groups of data points by a linear by a line, or in more dimension we can say a plane, then that is called as linear classification. Okay, the separation between the two groups is done by a linear feature, or linear feature, that is line in case of two dimension, or plane in case of three dimensions. So this is linear classification. Okay, now classification can also be in two categories. One is binary classification, second is multi-class classification. Generally multi means more than one, but not in machine learning. Okay, machine learning, multi means more than two, because for two classes we generally use binary classification. Okay, and multi-class classification means more than two. Okay, more than two group means multi-class classification, only two groups means binary classification. Okay, now you have seen this thing. If we separate two groups of data points and there are only two feature or two input, then we can do it by a simple line. But what if our input increases to 3? Okay, more than 3 we cannot visualize, but up to 3 we can visualize. Okay, so if our input increases from 2 to 3, we have to separate the data point with the help of a plane. Okay, and if the input features are more than 3, just like 4 or more axes, then the separating boundary is known as hyperplane. Okay, so again I am revising. So last week we have discussed about linear regression. Okay, now today we are discussing about linear classification. What is the difference? Linear regression, we have only one group of data point. Okay, we have only one group of data point, and what we are doing, we are fitting the best curve. Yeah, what we are doing, we are fitting the best curve. Okay, how we are doing this? We are doing this by RSS, that is residual sum of squares. Okay, so that is linear regression. Okay, if our RSS is we may like this line, we can try with different lines. Okay, and for the line for which the RSS is minimum, we called it as best fit line. Okay, today we are discussing about linear classification. Okay, linear classification, now we are talking about more than one group of data points. Earlier there is only one group of data points, that is why it was denoted by red dots, but here you can see there are more than one group of data points. We have denoted it one group by red dots, another group by blue dots. Okay, so linear classification means we will separate these two groups of data by a straight line. By a straight line in case of two inputs. If we have more than two inputs, that is three inputs, we do it by a plane. Okay, and if we have more than three inputs, that is four or more inputs, then we separate these groups of data points by hyperplane. Okay, now classification also, here we are only talking about two groups. Okay, but there can be cases in which the classification we have to do for more than two groups. Okay, so more than two groups means that classification is known as multi-class classification, and if we are doing only for two groups, that is here and all this, that is called binary classification. Okay, so this is the thing about linear classification. So is this clear to all of you? Any doubt in this slide?
It's fine up to now.
Okay, so nice. So yeah, so linear regression, the error we are calculating in terms of RSS, right? RSS, that is residual sum of square. What is residual sum of square? That is yi, that is the actual output, minus the fxi, that is the predicted output, whole square. Why we are taking square? Because yeah, and sigma for all the data points, that is sigma I equals to 1 to n yi minus fxi whole square. Okay, so why we are doing square? Because there can be some terms for which yi minus fxi is positive, there can be some terms yi plus yi minus fxi is negative. Okay, so if we just add up, what will happen is some error we will get lost. Okay, so that is why to encounter this, what we do, we square the things, that is yi minus fxi whole square sigma. Okay, now what about linear classification? How we will find the error? We will find the error by a thing called misclassification points. Okay, so here you can see this one is your misclassified point. Okay, so this you can say your error score is 1. Okay, if there is one blue point here also and one blue point here also, so you can say your misclassification score is 3. Okay, so by that you can find out the error in your linear classification. Okay, so this is all about linear classification. Now what is the problem about this linear classification? You can see by this case. Okay, this is x-axis is your age, and y-axis a person will take insurance or not take insurance. So it is encoded in such a way that person, if the person will not take insurance, that is denoted by 0. Okay, and if a person will take insurance, it is denoted by 1. Okay, so data points are plotted in such a way that if a person will not take insurance, it is denoted by 0, and if a person will take insurance, it is denoted by 1. Okay, so we can just put a line and we can classify this. But here here the problem is, earlier I have told about the misclassification score. Here this example, you can say the misclassification score is very much large. Okay, and also if you will say that for example, if you have put a line, okay, and if you have said that we will be regressing with the help of this line. Okay, so if we regress with the help of this line, and if we say that zero point 0.5 is our threshold value, that is below 0.5 we will consider our output as 0, and above 0.5 we will consider our output as 1. Okay, but you can see if you will take like this age. Okay, if you will take like this age and regress it, you can see that your answer will come below 0.5. that is you will be regressing it to 0. That is you will say that at the age of 40 the people will not buy insurance, but here you can say, you can clearly see that our actual output is at the age of 40 your people are buying insurance. Okay, so that is the problem of linear classification. We have more misclassification error, and sometimes our interpretability is wrong. Okay, so this is the problem of our this linear classification thing. So how to cope up with this? So to cope up with this, we have introduced this logistic regression. Okay, what the logistic regression do? It fits the data points very well. You can see here the data points, this line is not fitting at all. We are missing this data point, we are missing this data point, so the error will be very much large. Okay, so that is why linear regression will fail here. But if we will put a S-shaped curve in place of a straight line, you can okay, people are joining. Okay, yeah. So if we will fit a S-shaped curve in place of a straight line, you can see the data points fits very well. Okay, so this is known as logistic regression. What is the speciality of logistic regression? Speciality of logistic regression is, here the equation is y equals to mx plus c. Okay, mx plus c, that is straight line formula of the straight line, or equation of the straight line. Okay, so this is your model. But here logistic regression, we are fitting the curve by a function called sigmoid function. Sigmoid z equals to 1 plus 1 by 1 plus e to the power minus z. Okay, and e is a Euler number, that is 2.71828. Okay, now another speciality of for this function is here here the problem is here it is taking 0 and 1, but there can be some cases where the output will be not 0 and 1. But for sigmoid function, what it does is it converts the y-axis between 0 to 1. That is, the sigmoid function always results in a value between 0 to 1. Okay, so this is the sigmoid function. So, and this curve is known as logistic regression. Okay, now earlier for linear regression we have find out error by residual sum of square error. Okay, RSS. Again, what is RSS? That is yi minus fxi whole square and sigma for all the data points. That is sigma I equals to 1 to n. If we have n number of data points, yi that is the actual output minus fxi, that is the predicted output, whole square. So by that we have found out the error in case of linear regression. But in logistic regression we will do it by something called likelihood. So what is likelihood? We will see. Here you can see in this curve, you can see like in linear regression, if we fit a curve, we can fit a curve here, we can fit a curve here, we can fit a curve here. For this curve only, your RSS value will be minimum. Similarly for logistic regression, we have to fit some curves. We have to fit some S-shaped curves. Okay, so this is our first S-shaped curve, second, third, fourth, etc. And we have to find out, earlier we are dealing with RSS. Our target was to minimize the RSS. RSS should be minimum. Okay, minimum, MIN, RSS should be minimum. But here our likelihood should be maximum. What is likelihood? That we will discuss in the next slide. But now you just know this thing. For fitting a curve in our logistic regression, our RSS should be maximum. Okay, so our likelihood should be maximum. RSS should be minimum in case of linear regression, but here likelihood should be maximum to fit the curve. So this is the best curve. Why this is the best curve? Because it has maximum likelihood value. Okay, so this is the thing. RSS should be likelihood should be maximum if we want to fit a S-shaped curve or sigmoid curve in case of logistic regression. Okay, so is this clear?
Yeah. Yes, sir.
Okay. Okay, so we will go in some maths because yeah, maths is something important. So this is a maths about RSS. This is the maths about likelihood. Okay, so so likelihood here you can see this axis. This axis is actually probability. 1 means the person will buy insurance, 0 means the person will not buy insurance. So here or here you can see this is another curve. Here the mouse is not obese if probability is 0, mouse is obese if probability is 1. Okay, and we are also talking about two things, that is two groups of classes. Here you can see this is the first group of class, and here another group of class, that is this is a case of binary classification. Okay, so this curve is a S-shaped curve, but our target is to convert this into a straight line. How we can do it? We can do it by logit transformation. What is the logit transformation? Logit transformation is log of px divided by 1 minus px. Px is probability of that point belonging to that class, 1 minus px is probability of that point belonging to another class. Okay, so this is the thing. And if we divided px by 1 minus px and log and put a log to it, that is known as logit transformation. Why we are doing this? We are doing this to convert it into a straight line equation. You are very much familiar with this b naught plus b1x or whatever, b1x or beta no, beta x. That is, this is a equation for yeah,
Straight line.
yeah, this is a equation for
Yes, sir.
straight line. Okay, so that is what we have done. We have converted this probability axis, this is your probability axis. Okay, we have converted this probability axis into a straight line curve. Okay, and by this we can find out what is the probability in terms of that straight line coefficient. Okay, so how we can do that? We will just this is log e base px 1 minus px. Okay, so that means px by 1 minus px will be equal to e to the power beta naught plus beta 1x. Okay, and when we will solve this, we will find the px, that is e to the power beta naught plus beta 1x divided by 1 plus e to the power beta naught plus beta 1x. Okay, and if we divide by e to the power beta naught plus beta 1x, so we will get this. Okay, that is 1 by 1 plus e to the power minus beta naught plus beta x. Okay, now what is this px? You can question it. What is this px? Px is probability of the point belonging to that group. Okay, g equals to 1, that means group 1. Okay, so that is px. Now now we are talking about when the group was 1. Okay, now what if the group is k? So for that same equation, only this beta naught and beta 1 value, it will be for that k group. Okay, so only k we have implemented. Now this is not our thing. Our target is to find out the likelihood. Okay, so likelihood, how we will find out the likelihood? Likelihood will be given by this equation. Yeah, it is a bit unclear, but yeah, I will tell you. This L theta, okay, this is beta naught b, means coefficients, that means this is L theta. Okay, what is theta? Theta is same thing, beta naught, beta 1, beta 2, beta 3, all in a matrix form. So that is that we can say L theta. So L theta, this is multiplication sign, like sigma is for addition. Okay, sigma is for addition, this is for multiplication. Multiplication we will do from 1 to n. Okay, 1 to n. N is the number of data points. Earlier we do same thing, 1 to n. Okay, sigma we do first 1 to n. What we write? We write yi minus f x I and we do the whole square. Okay, that is our RSS.
But why do we take product here, sir, instead
Why?
of addition?
Yeah, why do we keep product here? It depends on the maths actually. Okay, because always see for this log thing, always we like to do product. Okay, so this is the thing. And probability, if we have two class probability, one is like obese, one is for not obese. So how we can do that? Pxi 1 minus pxi, that means probability of one class. 1 minus pxi means probability of the next class. So ultimately we have to multiply the two probabilities. So that is the only concept why we are multiplying here and why we are adding there. There we have to just add all the errors. Here we have to here it is called error. Okay, here it is called likelihood. Likelihood means probability of the point belonging to that class. Okay, so that is why pxi. And probability of that points not belonging to another class, that is why 1 minus pxi. Okay, so your likelihood function will be pxi. Okay, pxi, probability of point belonging to that class, into yi you can tell, or gi you can tell, whatever. Here the training points is given by x1 g1. Okay, if I tell the training points are given by x1 y1, so we can write this pxi yi, and then 1 minus pxi 1 minus yi. Okay, this is your likelihood function, and you have to do for all your data points. Okay, now here also, if we do this delta by delta rss divided by delta beta and equate it by 0, we will get our beta naught, beta 1, beta 2, etc. Okay, now here also, if we do the same things with respect to beta, we will get our beta naught, beta 1, beta 2, if we convert this pxi in this form. Okay, so that you can follow your lecture notes. That is done. So again I am telling, but here earlier rss we are minimizing the residual sum of squares. Okay, here we are maximizing the likelihood function. This is another difference. Okay, here because we are talking about probability of that point belonging to one class, so we are talking about, yeah, here we are talking about arg minimum arg minimum, and then rss. Okay, rss with respect to beta. And but here what we are doing is arg max likelihood, sorry, max likelihood, or somewhere we can also tell ln of likelihood, that means log of likelihood with respect to beta. Okay, so this is the difference. Earlier differentiation with respect to rs, with respect to beta, we will equate to 0 and find so that we can find the minimum rss. Here differentiation with respect to beta, so that we can differentiation of likelihood with respect to beta, so we can find the maximum likelihood. So this is the difference. So this is the formula for your likelihood. Okay, now, yeah, now these things can be written in log form. That is, yeah, if you will write this in log form, what will happen is this pi will change to sigma. Okay, this pi will change to sigma, because then you have to because whenever you are taking log on both sides, these things will add up. Okay, these things will become yi pxi plus 1 minus yi 1 minus yi 1 minus pxi. So that is adding up. So that is why you can write sigma if you are doing log of that likelihood. So this is the thing. Okay, is this clear, this slide, how to
Yeah,
find
yes,
out
sir.
likelihood? Yeah, I think it is clear.
Yes, sir.
Okay, so logistic regression, yeah, more formula. For more formula, you have to delve it in your lecture notes. You have to also, I have share one book for you all in my that folder. So for more maths you can certainly look into more maths, but this is the main thing. Okay, this is very important for question part, so that is why I have more focus what is likelihood and how we are jumping from RSS to likelihood in case of logistic regression. Okay, now we will see the next thing called linear discriminant analysis. Okay, so LDA. Now, linear discriminant analysis, like PCA, if you will remember in your linear regression or your regression part, we have discussed one thing called PCA, principal component analysis or principal component regression. Okay, and now here, why we have done that? We have done that to reduce the dimensionality, because we have issue of dimension. That is, whenever we have more than 3 or like 100 of inputs, so what we are interested to reduce the dimensionality of the data. That means we are interested in reducing the inputs. Okay, how we are reducing the inputs? We are reducing the inputs in with respect to the inputs that are very much correlated. We are combining those and making one input. Okay, so by that we are reducing the input, not just dropping it. If we drop it, then that is called feature selection. Okay, if we drop it, that is called feature selection. If we don't drop it and combine the input to make less dimensionality, that is called feature extraction. So again, in case of this classification method or linear classification method, for dimensionality reduction we have this linear discriminant analysis. Okay, yeah, we have this linear discriminant analysis, LDA. Yeah, LDA. It is a dimensionality reduction technique crucial in modeling differences between the two classes. LDA is like PCA, yeah, but it focuses on maximizing separability among known classes. Because earlier, our target is different here. Earlier, we are just regressing our data. Okay, but here our target is to separate the group of data or group of classes. So, and that is why our focus will be to maximize the separability among these known classes. Okay, now if I show you by example, here we are reducing a 2D graph into a 1D graph. So how we can do this? We can do this by feature selection. Okay, how we can do this? We can do this by dropping one axis. That means we have here two axes, gene x and gene y. If we just drop one axis and project all our data point in one axis, so that will reduce our dimension. Okay, that will do a dimensionality reduction, but that we don't want it. Why we do not want it? Because here we are completely dropping off one input. Okay, so that error will be more. If we are just completely dropping off one input, our error will be more. Okay, so next method what we are doing is we will do it by linear discriminant analysis. How we will do it by linear discriminant analysis? We will find a line, okay, in between our data points, so that whenever it is projected, whenever our known data points are projected on that line, we can separate the group of data. Okay, so that is the idea between LDA. So again I am repeating, like we have two genes. Okay, gene X and genes Y. Okay, yeah, we have two genes, gene X and gene Y. Okay, so one method is directly dropping of the input, so that is known as feature selection. Okay, so the problem is if we directly drop off one input, like if we directly drop off Y, all the information of that particular input is lost, and affect on the outcome of your machine learning model. Okay, so that we do not want. What we do want, we do want to create an axis. If we project our data on it, it will give the feature of both our line. And also in case of linear discriminant analysis, we can classify or we can maximize the separability among these two classes. So here you can see there are two classes. One class is denoted by green dots and another class is denoted by red dots. So if we found a line such that the line is created in such a way that whenever we are projecting this point on this particular line, we can very well maximize the separability among the two classes. You can see there this by doing this we are not able to separate our classes well, right? But whenever we are projecting all this data point on this line, here we can certainly classify well, certainly classify these two groups well. Only we have only one misclassification data or misclassification error. Okay, so this is about linear discriminant analysis. Now the question is how to fit or how to find out this new axis. Okay, so our yeah, so the question is how LDA creates this new axis. So the new axis is created according to two criteria. One is we have to maximize the distance between the mean of the two data. Okay, so you can see about this two data, we have one mean in we have one group of data in green color and we have another group of data in red color. Okay, so the mean of this group of data is mu, denoted by green mu. Okay, and the mean of this group of data is denoted by red mu. Okay, so our first target is to maximize the distance between the mean. So how you can do that? We can just subtract between the two mu. Okay, that is mu I, mu green, or you can say, if I tell it this mu g and this mu r, so mu g minus mu r whole square. Okay, again why we are talking about the whole square? We want to just suppress the idea of signs. Okay, whenever we are squaring the data, the sign will always be positive. So that is the idea to square the thing. Okay, so what we are doing, mu g minus mu, and our first target is to maximize the distance between the mean. Okay, so the distance between the mean, mu g minus mu r, that is we can also say as d. Okay, so our first target is make this mu g minus mu r ideally large. Our second target is to minimize the variation, which LDA calls scatter and is represented by s square within each category. So each category we have some scatter. Scatter you can tell something about. You can say this is a variance. Okay, variance is what? Standard deviation square. Okay, that is why it is denoted by s square. Okay, so here you can see the variance of this data, and that is green data as green s square, and here variance of this data is red s square. Okay, so green.
So,
Yeah, hello.
how to get the equation of this axis, new axis, after writing Fisher criterion?
Equation you can see your lecture notes, there you can find out. Okay, actually this is a Gaussian distribution. Okay, Gaussian distribution, again you have to find out that logit function, that is in the top you have to put one class, and in the bottom you have to put one class, and then here all this, LDA consider your data points to be Gaussian, and you know there is a formula for Gaussian distribution. Okay, so that distribution, when you will put in that formula, so you will get the equation. Okay, we will solve some
And which
question.
formula should I put the equation?
Yeah, we will discuss some question, with that you can get an idea. Okay,
Yes, sir.
okay. So this is the thing. For more for how to put it accurately, you can consider your lecture notes. Okay, okay. So so our next target is to our next target is scatter within the group, that is scatter within the green group, or as well as scatter within the red group, that should be ideally small. Okay, so first target is maximize the distance between the two data groups, and second, minimize the variation within the two data group. Okay, so this is this is also called as variation within the classes. So variation within the classes we want small as possible, and this is called variation between the classes. Why it is called variation between the classes? Because we are talking about one new we are discussing the mean of two classes, so that is why variation between the top is variation between the classes, and the numerator is called variation between the classes. The denominator is known as variation within the classes. So variation between the classes should be ideally large, and variation within the classes should be ideally small. So that is the idea how we create our new axis. So any doubt in this?
So
Okay.
far, good, sir.
Okay. Okay. So yeah. So this is hello.
Yeah, please go ahead.
Yeah, yeah. So yeah. You I have already told you this. This LDA, consider your data points to be a Gaussian distribution. Okay. So Gaussian distribution. Okay. Let me see this. Yeah. Gaussian distribution. The probability of your data point belonging to a class K is given by this. Okay. Fk Fk is your probability density function. Okay, pi k is your sample size. Okay, and here yeah, here we are here this is the yeah, top top is always for one class. Okay, and below this is the sum of all the classes. Like you have L class, so you have L class from 1 to L, that is first class plus second class plus third class, dot 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 to L class. So this is your probability is that only, right? That what which class we are interested in divided by total all the classes. So this is the probability of a data point belonging to that belonging to that particular group. Okay, so this is probability. This is also called as discriminant of the data point. Okay, discriminant of the data point belonging to a particular class. Okay, now suppose that we model each class density to a multivariate Gaussian. Okay, this is the Gaussian function. Okay, this is the Gaussian function. Now linear discriminant analysis LDA arise in special case when we assume that two classes have common covariance. Yeah, your covariance should be common. This is actually covariance. So your covariance should be common. That is the assumption of LDA. So if we compare two classes K and L, it is sufficient to look that log ratio, we see that. So again we will find the logit function. What is logit function? Logit function is probability of one class divided by probability of another class if we have two class in case of binary classification. So whenever we will do this logit function, you will be reaching to this equation. Okay, log fkx divided by log flx plus log pi k and pi l. This is related to density function of that particular group of K group, and L density function of that L group, and log pi k and pi l, this is related to your sample size. Okay, sample size of K and sample size of L. Okay, whenever you will solve it, you just put your fk in here and fl here. When you will solve it, you will be reaching to this equation. So this is the boundary equation of your two groups. Okay, this linear log function that implies the decision boundary or that boundary equation of K and L, the set where PRGKX is equal to PRG equals to L, X equals to X. Okay, whenever your log function, logit function will be equal to 1, logit function will be equal to 1, that equation we will call it as the boundary equation. That means log whenever that will be equal to whenever that this thing will be equal, or whenever we, okay, not 1, sorry, this will be 0. Okay, whenever your logit function will be 0 or whenever your two probabilities will be equal, that thing is no, that thing will give the decision boundary between the k and l class. Okay. Now this can also be written in terms of a discriminant, or this thing whenever you will solve it or make this thing equals to 0, this you will be getting this thing. Okay, xt is that matrix of all your inputs, and mu k is related to that mu k is related to mean of kth class minus half of mu k t sigma mu k plus log of pi k. Pi k is related to your sample size of k. Okay, so this is known as discriminant with respect to k class. Okay, if discriminant with respect to l class, you have to interchange k with respect to l. Okay, so this is some equation about your this LDA. Okay, is this clear?
Yeah, can you please rub this black handwritten so that we can take a equation clear screenshot, please,
Okay.
if you don't mind.
Yeah, this equation.
Yes. Yeah, that's it. Thanks.
Okay, so for more details, kindly go into your lecture. Also, I have shared a book called Statistics of I think Statistical Learning something. So you please Elements of Statistical Learning (ESL). So in that book also it is given in detail. So for more maths, you have to follow some of the literature. Okay. So this is the theory part of this class. So any doubt in today's theory part, you can ask. At least you got some concept why we are using it, that you got at least. Any doubt?
Sir, can you show the equation of
Equation, last equation.
Yes, sir. Yes, sir.
So that logic,
Does this
why are
LDA
we taking the
Yeah,
ratio?
can
Can
you
you
please
just tell that
repeat?
again? For the logic, why are we taking the ratio? Can you just tell that again?
Logit transformation means ratio between two probabilities. If we have two classes, na, so probability of that point belonging to one class divided by probability of same point belonging to another class, that is logit transformation. Here also here you can probably understand well. Okay, yeah, here you can probably understand well. This is logit function, right? Logit function is log of px divided by 1 minus px. What is 1 minus px? 1 minus px means probability of that point belonging to another class. Like we have here two classes, right? We have all this two example. You can see we have two classes. One, the person will buy insurance, and second thing, the person will not buy insurance. Okay, so we have two classes, right? So probability of data point belonging to one class divided by probability of the same data point belonging to another class. So how we can find out probability of same data point belonging to another class? That we can do that by 1 minus px, because if we sum up the probability, it will be 1. So that is why 1 minus px. If same data point is belonging to another class, there 1 minus px. So that is logit function. Okay, logit function
Yeah.
is for LDA, this is the logit function. If we are considering two classes, right, g equals to k means the x point will be belonging to k class. Okay, x equals to g equals to l, that means the x point will be belonging to l class. So this is known as logit transformation. Okay, and your discriminant, whenever you will find yeah uh, uh, the point will be on decision boundary. Like here there is one set of data point, here there is one set of data point. So your data point will be on decision boundary only when your this probabilities will get equal, or logit function will be equal to 0. Okay, this is the concept.
Okay.
Does the logic will works only for two classes or what? Or
Yeah, logit function, yeah, logit function we visualize it for two classes only.
okay, okay.
Okay, so let's move into the questions. Okay, today's these are the three things we have discussed. So we will do some of the question related to this. Okay, so for question answer, kindly whenever I
Hello?
will be showing you the
Hello? Samar my number one sir.
yeah, whenever I will be showing you the question, kindly try to guess it, and then we will discuss the solution. Okay. So this is the first question: which of the following statement about the decision boundary and boundaries and the discriminant function of the classifier is are true? In a binary classification problem, all points x on the decision boundary satisfy del 1 x equals to del 2 s. That means this is the discriminant of x, this is the discriminant of first group, and this is the discriminant of second group. That means this is nothing, this is that probability g equals to, you can say g equals to 1 and x belonging to x. Okay, this is the probability. Okay, this is the discriminant. Okay, now for this you can tell PR g equals to 2 x equals to x. Okay, this is the thing. So this is the first option. In a binary classification, all points on x on decision boundary satisfy del 1 x equals to del 2 x. Second is, in a three class classification problem, all points on the decision boundary satisfy del 1 x equals to del 2 x equals to del 3 x. C is, in a three classification problem, all points on the decision boundary satisfy at least one of del 1 x equals to del 2 x, del 2 x equals to del 3 x, and del 3 x equals to del 1 x. And D, let the input space be Rn if x does not lie on the decision boundary, there exists epsilon greater than 0 such that inputs y satisfying y minus x less than epsilon belongs to the same class. So any guesses? Yeah, hyperplane, right? Hyperplane we are using for, like if we have only two inputs, then we are telling this is a linear classification. We are separating our data points by a line. Okay, if we have more than two inputs, that is three inputs, then we are separating our data points with the help of a plane. And if we have more than three inputs, then we are separating our data point by something called hyperplane. Okay, that we cannot visualize because it is more than 3 dimension, that is 4 dimensions, so that we cannot visualize, but that is a hyperplane. Okay. Okay, someone was telling AC, AB, AD. Okay, so thing is, always I have told you, if we are talking about our decision boundary, in that decision boundary what happens is our discriminant function will be equal. Like if this is a thing and we have two classes, here one type of class and here one type of class, and we are taking one point on a decision boundary, then this probability of that this is, let's say, group 1 and this, let's say, group 2. Okay, so probability of this point, or let me tell this by star, probability of that star point belonging to belonging to belonging to group 1 will be equal to probability of this star point will be belonging to group 2. So option A is right. So now what will happen in a three classification problem? Now how we can form a three group classification problem, or multi classification problem? Now here, if this is one group, this is another group, and this is another group. Now how we can separate a hyperplane? If we are only putting one plane, then we are not completely separating our data points. Okay, so this is a case of masking. Okay, what is masking? Masking happens if we are if we have more than two if we have more than this two group of data, and we are directly separating it by a linear classifier. What will happen is we can separate one group, but we cannot separate the other two well. Okay, so that is known as masking problem. So how we can separate this two? We can separate this two by something called this. Okay, by something like this. Okay, so we have three lines. Okay, we have one line, we have second line, we have third line. So let's say this is our group 1, this is our group 2, and this is our group 3. Okay, so for group 1, what will happen is del 1 equal to, if we say a point on this boundary, then what will happen is del 1x will be equal to del 3x. Now for this boundary, del 1x will be equal to del 2x, and for this boundary, del 2x will be equal to del 3x. That means this is also correct. Okay, so A is correct and C is correct. And what about the if x does not lie on the decision boundary? Okay, if x does not lie on the decision boundary, and there exists epsilon such that all inputs y satisfying y minus x belongs to the same class. Y minus x less than epsilon will be belonging to the same class. Now we don't know anything about this epsilon. This is the problem. So as we do not know anything about the epsilon, your data points can get into both these groups. Okay, so that is why we cannot tell true about this D. So your okay. So yeah, if the epsilon if a point does not lie on the decision boundary, it lies in the interior region corresponding to one of the okay. If a point does not lie on the decision boundary, here it is telling this thing only. If a point does not lie on a decision boundary, then it will be either in one class. Okay, that is the thing it is telling. So that is why option D is also correct. Okay, so your correct answer is A, C, and D. Okay. Okay, so let's get into the question number second. Yeah, here I think there is missing. This is PXI. Okay, PXI. Okay, the following table gives the binary ground truth yi. Okay, yi for 4 inputs xi. We have logistic regression model with some parameter value and compute the probability pxi. So we have computed the probability. Compute likelihood of the observing data given this model. So what is likelihood? Likelihood is your likelihood is your likelihood is your yi pxi into okay.
This is 0.8 into 0.4 into 0.8 into 0.9, is it?
Yeah, this is 0.8, 0.4, 0.2, 0.9. Is it not visible?
And now it is visible.
Visible.
Okay, let me see this. It is visible, right? Yeah, I think it is visible.
Yeah,
Right,
yes.
yeah.
Please go.
So this is pxi yi 1 minus pxi and y 1 minus yi to the power. Okay, and we have to do this for all our data point, that is I equals to 1 to n. Okay, and we have to multiply it. We don't have to sum it, we have to multiply it. Okay, so that will give your likelihood. Okay, so how we will do this? It is very simple. Okay, so how you will do this? You will take one point at a time, and you will do this like for first point 0.8 to the power 1, and 1 minus 1 is 0, then we don't have to think about it. Okay, now let's go to second point, 0.4 to the power 1 and 0.4 to the power 1, okay, into 0.4 to the power 1, okay, 0.4 to the power 1. For this, 2 to the power 0 is nothing, and 1 minus 0.2 is 0.8 to the power 1, okay, and into this is 0.4, okay, and into last one is 0.9 to the power 1. Okay, so 8 into 4 into 8 into 9, whenever you will do it, you will be reaching to option B, okay, that is 0.230. Okay, is it clear how we are
So
doing it?
what about the second part? Like 1 minus p of x
Yeah,
raised to
but
1 minus
yeah,
y.
yeah, yeah. I have also do this. See, let's take this point. Okay, let's take this point. So px is 0.8, right? Clear? To the power y1. Y1 is
Yes.
1. Clear? Into 1 minus
Yes.
pxi, that is 0.2. Right? But here the power is
Okay.
1 minus 1. 1 minus 1 is
Okay.
0.
Okay.
That means 1. So
Okay.
that is why only 0.8. Okay, now let's get into the second point. Second point is 0.4. Okay, so 0.4, same thing, 0.4 to the power 1 into 0.6 to the power 1 minus 1 is 0. So only 0.4. Okay, now third part is 0.2 to the power 0. Okay, 0.2 to the power 0, that means 1 into 1 minus 0.2, that is 0.8 to the power 1 minus 0, that means 1. So 0.8 to the power 1 is 0.8. So this is the third thing. And fourth thing, again 0.9 to the power 0.9 to the power 1, and into 0.1 to the power, yeah, 0.9 to the power 1 and 0.1 to the power 0. So this again will represent, so 0.9. Okay, so when you will multiply it, you will get the result. Okay, is it clear?
Yes.
Yes.
Thank you.
Sir, if it is zero and the label is zero, then we have to take the reverse, right? Like label
Label
one.
label is 0 means 0 0, like this, 0 0 1 0.
Yeah,
Yeah, 0 0, same formula you have to apply. Then what will happen?
point two
0.8 to the
into.
power 0 and zero point 0.2 to the power 1. Okay, 1 minus 0 is 1. Okay, so here will come
No,
zero
no,
point 4.
sir. No,
Yeah,
sir. In this question, it's given like we have a logistic regression model with some parameter values
acha
that
acha.
computes the probability that the label is 1, right?
Yeah, yeah,
If
yeah,
it is 0,
yeah, yeah, yeah. If the
it is
label,
0 and the same is given.
yeah, if the label is 0, right, label is 0, then yeah, if the label is 0, then pxi will be for 0 only, right? So pxi will be for 0, so 1 minus pxi will be for 1. Okay,
Uh, Means
yeah,
1 minus pxi will be for 0. Means
uh,
first.
yeah.
Correct. So first we have to take point 0.2 into point 0.6 into point 0.2 into point 0.1, right? In that case,
Yeah, pxi label will be 0. So label, yeah, pxi will be for 0, right? Pxi will be 0. Pxi will be 0. Then we have to go for 1 minus pxi. So here will be 0.2, zero point 0.6, like this, zero point 0.8 and zero point 0.1. Okay.
Yeah.
Okay. So let's
Y-
move to the third question. It is clear, right? Likelihood.
yes,
This is the
yes.
formula.
Yeah.
Yeah.
Yes.
So consider a modified form of logistic regression given below, where k is a positive constant and beta naught and beta 1 are the parameters. Okay, so this is log 1 minus px divided by kps. K must be some positive constant here, and we have to find px. So this is very simple. This is just maths. How you will do it? This is log 1 minus px, kpx. So 1 minus px, 1 minus, yeah, let me show you, yeah, 1 minus px divided by kpx will be e to the power beta naught minus beta 1x. Okay, now simply you just multiply it. 1 minus px will be kpx e to the power beta naught minus beta 1x. Now take the px common. Okay, so whenever we will take the px common, this thing will be common. Okay, 1 plus k e to the power beta naught minus beta 1x, and by that you can find out the px. Okay, so this is your which option? Beta 1x, beta. Okay, this is your option B. Okay, so option okay, is it option C? Beta naught. Okay, k is there. Sorry, k is there. So this is your option C. Okay, so is this clear? This is simple maths, right? This is
Yes.
only, this question is only meant so that you can convert your logit function to a straight line. Okay, and find out the probability, or do the reverse. Okay, so that is for this question. That means this question is
One.
to explain you this. Okay, how you have done this. How you can find the probability if your straight line equation is given. So this is the thing. Is it clear?
Yeah. One question. So in the previous question, the labels were zeros and ones, right? So if those are not zeros and ones, then should we do one hot encoding first and then do like for logistic regression?
Yeah. Here we have logistic regression model with some parameter value that computes the probability. Probability is already calculated by our logistic regression model. Okay, if our probability is not calculated, then we have to calculate our probability with our logistic regression model first, and then we by that we have to find the probability, and then we have to solve for this solve the likelihood of that model. Okay.
Okay.
Which of the following statement about logistic regression is are true? It learns a model for probability distribution of the data points in each class. The output of a linear model the output of a linear model is transformed to the range 0 1 by a sigmoid function. The parameters are learned by optimizing the mean squared loss. D. The loss function is optimized by using an iterative numerical algorithm.
May you know what is iterative numerical algorithm means?
Yeah, iterative numerical algorithm means you have to compute your beta again and again. Okay, so that is
Okay.
iterative. So we do it by applying some kind of weights to it. So kindly please check your lecture, you will get the full concept there. So
Okay.
there you will see in one point beta new something written. Okay, beta new will be something beta old plus some of the
Okay.
terms.
Okay.
Okay,
Okay.
some weights with the
Newton-Raphson method, right, sir?
yeah. So that is the thing. Okay, so your right answer here is B as well as D. Okay, so B, the output of the linear model is transformed to the range 0 to 1. That is the probability. Okay, by a sigmoid function, and D, the loss function is optimized by using an iterative numerical algorithm. Okay, so unlike LDA, logistic regression does not. Yeah, this probability distribution is for LDA. Okay, we have just discussed in the last slide. We have discussed it learns the model for probability distribution, that is for LDA. Okay, the optimal parameters are computed by maximum log likelihood and not by minimum this mean squared loss. Okay, we will compute the parameter by maximum log likelihood, that is already discussed in my theory part. Okay, that is arc max with respect to your theta or beta, whatever you will tell, and we will do for log likelihood. Okay, ln L. So that is the thing. So your correct answer will be B, option D. Okay. Okay. So it is clear, right?
Yeah, yes, please.
Okay. So again something is missing. Okay, this is f k of x. Okay, so consider a Bayesian classifier for a three classification problem. The following tables give the class condition density fkx for the three classes k equals to 1, 2 and 3. That means we have three classes numbered as 1, 2 and 3 at some point x in the input space. Note that pi k denotes prior probability of class k. Which of the following statement about the predicted label at x is are true? Okay, if the three classes have equal priors, the prediction must be class 2. If pi 3 is less than pi 2 and pi 1 is less than pi 2, the prediction may not necessarily be class 2. If pi 1 less than 2 pi 2, the prediction could be class 1 or class 3. If pi 1 less than pi 1 less than, this must be pi 2, right? Pi 1 less than pi 2 less than pi 3, the prediction must be class 1. Okay, so this is the explanation. So for the Bayesian classifier is your last thing, okay, that we have talked about in that Gaussian distribution thing. Okay, the prediction is given by arg max xk fkx pi k. Okay, so by this we are getting the prediction. Okay, so if you will see in option A and B, what has been given in option A and B, if the three classes have equal priors, if the three classes have equal priors means pi 1 equals to pi 2 equals to pi 3, then your if pi 1 equals to pi 2 equals to pi 3, then your this argmax will be fkx pi k. That means f1x equals to f2x equals to f3x. If the three classes have equal priors, the prediction must be for yeah, if the three classes have equal priors means pi 1 equals to pi 2 equals to pi 3, then your prediction will be only dependent on fk, because pi is equal for all the classes. So fk, here in the table you can see that fk is maximum for class 2, so that is why your prediction must be for class 2. Okay, now if we will see the option B, if pi 3 greater than pi 2 greater than pi 3 and pi 2 greater than pi 1, the prediction may not be necessarily class 2. So in option B you can say that if here you can say that pi 2 greater than pi 3, that means if pi 2 greater than pi 3, then as f 2 is greater than f3, if pi 2 is also greater than pi 3, then the prediction will be class 2. Similarly, as f2 is greater than f1 and also pi 2 will be greater than pi 1, then the prediction will be necessarily class 2. So this option is incorrect. Okay, this option is incorrect. So A is correct. Okay, A is correct, B is incorrect. Now if pi 1 lesser than 2 pi 2, okay, the prediction could be class 1 or class 3. Now if pi 1 less than 2 pi 2, then what will happen is f1x pi 1 will be greater than f2x pi 2. So the prediction, if f1x pi 1 greater than f3x pi 3 and class 3 otherwise. Okay, so let's see if pi 1 lesser than 2 pi 2. So what will happen is pi 1 lesser than 2 pi 2, let's say pi 1 is 1 and pi 2 is 2. Okay, so pi 1 is 1 and pi 2 is 2. That means 2 1 is lesser than 4. Okay, very good. 1 is lesser than 4. So let's say pi 1 equals to 1 and pi 2 equals to 2. Okay, so pi 1 lesser than pi 1 is lesser than 2 pi 2. Okay, pi 1 is lesser than 2 pi 2. Now if pi 1 is lesser than 2 pi 2, what will happen is pi 1 equals to, let's put pi 1 equals to 1 and pi 2 will be 2 pi 2 is 2, so 2 into point 2 means point 4. So yeah, so your okay, we have to assume a very small case here. Okay, so pi 1, let's say point 5 and greater than 2 into pi 1 lesser than 2 into 0.55, point 6. If we say 0.5 and 0.6, what will happen? 0.5 and 0.6, there also 0.75 and 1.2. So that there also this there also f2 f2 will be greater. Okay, there also f2 will be greater according to me. So then could be class 1 or class 3. So no, the C option is not correct according to me, because pi 1 is lesser, right? Pi 1 is lesser than 2 pi 2. So pi 1 is lesser than 2 pi 2 means pi 2 will be pi 1 by 2 is lesser than pi 2. Pi 1 by 2 will be lesser than pi 2. Okay, pi 1 by 2 will be lesser than pi 2. Okay, and pi 1 by 2 is lesser than pi 2, then pi 1 into 0.15 and okay, 0.15 pi 1 and 0.2 pi 2. Okay, 0.2 pi 2. Okay, so if pi this is the case, pi 1 by 2 is lesser than pi 1 by 2 is lesser than pi 2. Okay, pi 1 by 2 is lesser than pi 2. If we multiply 0.15 here, 0.15, so 0.15, so 0.15, so this is becoming 0.15 pi 1 is lesser than 0.3 pi 2. Okay, 5 is
Actually, if pi 1 is greater than 2 pi 2, then the option C is correct.
yeah, here the option C is not correct, right?
Yeah,
This is
here the
yeah, so here's something.
because in your solution 5 explanation itself, the f1 of x pi 1 is greater than f2 of x pi 2.
Yeah,
I
yeah,
guess there is something wrong in the question. That is
yeah,
the
yeah,
less than
yeah.
symbol.
Yeah, that is the problem. There is some problem with option C, and you can check this with option D also. So option A you already have understood, right? And option B also understood. Please check with C and D. There is some problem, I think. So that is why only focus about A and B. Okay, there is some problem with C and D. Okay, so this is the thing. You got the concept, right? How to do it? Fk pi k, and you have to compare, like pi 1 is greater, pi 2 is greater, that is given. Like here pi 1, pi 2 and pi 3 all are equal. Okay, and fk is given. Okay, so as fk is given, f2 is greater than f1 as well as f3, and pi is equal for all this. So this will be your class 2. So option A is correct. Now what about option B? Option B, again pi 2 is greater than pi 1 as well as pi 3, and also f2 is greater than f f2 is greater than f3 and f1. Okay, so option B is wrong. Okay, and please check about C and D. C is, I think, C is should be wrong. Okay, she should be wrong. And check about D is also, there is some problem with the question. Pi 1 pi
D
1,
is also wrong actually.
yeah, pi
So we
1
need to
pi
check.
1 is written. So again,
Yeah,
D is, there
again.
is some problem with this two thing. So you only focus about A and B. So out of A and B, let's see, out of A and B, A is your correct answer. Okay, and B is your incorrect answer. Okay, is it clear?
Yeah.
Okay, so let's move on to the next question. Okay, so this is the next question. The following table gives the binary label yi for 4 points x1 x2 I, where I varies from 1 to 3 4. That means we have 4 data point, 1 2 3 4. Okay, so this is our n. Okay, n is number of data points, so we have 4 data points and 4 data points with 2 inputs, that is, this is p. Okay, so that means p equals to 2. P is number of inputs and n is your data points, 1 2 3 4. So among the given option, which set of parameter value beta naught, beta 1 and beta 2 of a standard logistic regression model. So pxi is also given, that means pxi is given. So that is beta yeah, b1, this will be x1, and beta 2 x2. Okay, so this is pxi equals to 1 by 1 plus e to the power minus beta naught plus beta 1 x1 plus beta 2 x2 results in highest likelihood for this data. So highest likelihood, how you will find it? Yeah, whenever you are taking log, you have to do the sigma thing. Okay, earlier as we are not taking log, so we are doing the pi thing. That means we are just multiplying all the likelihoods. Okay, but here as we are doing the log thing, so we have to sum up the likelihood. Okay, so this is similar to this only, very similar to this. Is that question? Yeah, this is very similar to this. Here only we have taken log on both sides. So log L will become, what log L will become? Sigma. Okay, sigma yeah, sigma yi log pxi plus sigma 1 minus yi 1 minus yi log of 1 minus pxi. So whenever we will do this log, the equation will be changing in this form, that is yi sigma yi log pxi plus sigma 1 minus yi log of 1 minus pxi. Okay, that will be your sigma. So again we have to find out beta such that our log function will be maximum. So we have to try and error all the 4 option. So first you should start with beta naught. First you will be starting with this option. So in this option, beta naught is 0.5, beta 1 is 1, and beta 2 is 2. Okay, and x1 is 0.4, and x2 is minus 0.2. So we are doing it for first data point. Okay, so whenever you will do it, you will get a pxi, and then you get a pxi. So this is the same equation. Yeah, here it is written in a little bit different form, but this is the same equation. How this is the same equation? When you will see this now. So yi pxi log of pxi yi log of pxi minus yi log of 1 minus pxi. So yi log of pxi, and here is log of 1 minus pxi. So this you can take common, log of 1 minus pxi. Whenever you will take log of 1 minus pxi common, that is 1 minus y1. So your equation is same thing, yi log of pxi minus 1 minus yy log of 1 minus pxi. So same thing, okay, same equation here, that same equation that just I have explained, same equation, okay, just they have written in a bit different form, that is the thing, same equation. So you got your pxi, you have your yi, so you can find out the for this point you can find out the log likelihood. Okay, similarly you have to do it for this point, this points and this points, and add up all the points. Okay, so whenever you have add up, you will get a log likelihood function L1. Okay, say L1. L1 is done for this beta naught, this beta 1 and this beta 2. Similarly, you have to find L2, L3 and L4. How L2 can be find out? L2 can be find out when you will take all these beta values. So first, for finding out L2, you take all these beta values. You put here beta naught equals to minus 0.5, beta 1 equals to minus 1, beta 2 equals to 2. Okay, x1 will be equal to 0.4 and x2 will be equal to minus 0.2, and you find the pxi. You have found the pxi. You know this yi, that is 1, and minus yi 1 minus 1 minus pxi, that is you have just found. Okay, that is for first data point. Similarly, you have to do for second data point, third data point, fourth data point, and then to add up, and by that you will get a L2. Similarly, you will get a L3, you will get a L4. You have to see for uh, which uh, uh, which is the greatest, that is which L is the greatest. So here you will find out that L3 will be the greatest among all this L1, L2, L3 and L4. So that is why our this beta set of values will be optimum. Okay, so C option will be correct. So is this clear to all of you how to solve the question?
Can you repeat, sir? I can get.
Yeah, please. Yeah, I will repeat. So, yeah, you have this pxi thing. Okay, you have two inputs, x1 and x2. You have a predicted output y. Okay, so this thing is clear, right? And you have four data points, 1, 2, 3 and 4. Is this clear, right?
Yes.
Yeah, this is clear. So you remember the RSS. How we find out that beta is perfect for a RSS? How we find out that? We have do I equals to 1 to n, and what we do, yi minus fxi, and we do the square of it. Okay, this is our RSS. Okay, but this RSS is for 1. This RSS 1 will be for F1. Okay, how F1 is formed? F1 is formed by beta naught 1 and beta 1 1. Okay, you remember this question? Okay,
Yeah.
yeah, you remember this question, right? This fx1 will be found for beta naught 1 and beta 1 1. Okay, by that you will find the RSS, RSS1. Similarly, you will find the RSS2, RSS3, RSS4. Which RSS is smallest? Okay, for that you will say this beta value is optimum, or this is the best fit line. Okay, so
Yes.
that is for our linear regression. Now what about logistic regression? Logistic regression, we have to maximize the likelihood. Here we are minimizing the RSS, there we will maximize the likelihood. What is our likelihood equation? This is our likelihood equation, or in short this is our likelihood equation. Okay, log likelihood equation, that is sigma, yeah, let's put sigma for all, sigma I to 1 to n yi log pxi minus minus 1 minus yi, 1 minus yi, okay, let me delete it so more clear. Yeah, sigma yi log pxi minus 1 minus yi, uh, 1 minus y 1 minus y log 1 minus pxi, that is your log likelihood. Log likelihood we have to maximize, so we will be finding four log likelihood. So our first log likelihood will be from this one. Okay, from this option. How? We will put the beta naught value of 0.5 here, beta 1 1 here, beta 2 here. Okay, and we will find the pxi. How we will find the pxi? Beta 1 x1, so we will be 0.4, and x2 for minus 0.2. So that will be for our first point. Okay, similarly we will do for second point, third point, fourth point, and add up all this log likelihood. Okay, when we are adding all this log likelihood, we will find log likelihood L1. Okay, this will be a log likelihood L1. Similarly, we will find log likelihood L2. How we will find log likelihood L2? We will put this beta values here. Okay, now our beta value will be minus 0.5, minus 1 and 2. Okay, minus 0.5, minus 1 and 2. For the point 1, that is 0.4, and minus 0.2, and we will find the pxi, and then we will find the likelihood. Similarly, for the second point, third point and fourth point, we will find pxi, and we will be putting in the equation, and whenever we are adding for all this likelihood, we will get L2. Similarly, we will get L3, and we will get L4. We will see which log likelihood is maximum, and we will find that L3 will be maximum. So as L3 will be maximum, this is our optimum beta. Okay, beta naught 0.5, beta 1 1, and beta 2 minus 2. So is it clear?
Yeah, yes.
Okay, so any
Thanks.
doubt in this question, please? Anyone, any doubt in this question? Log likelihood, how to calculate log likelihood, how we have computed
So
the optimum beta.
without
Yeah, yes.
without that rearrangement itself, we can compute this, right? Can calculate
Without rearrangement. What
whatever
rearrangement?
the bottom one, what you are showing, right? That you are taking log 1 minus p of x outside or something.
Okay. So you are telling we should not take log, we should just multiply. Yeah, definitely. Definitely we can do that.
Okay.
Without taking log, just multiplying it, we can also do that. That means you are telling that we should apply this formula, right? Yeah, this formula, right? Yeah, absolutely, you can
Okay.
you can solve by this.
Okay.
Here also you have to see which log likelihood is maximum, and that will be your beta option. Okay. Okay. Now move on to the next point. Next question: which of the following statement about two class LDA model is are true? It is assumed that conditional probability density of each class is Gaussian. Option B, a different covariance matrix is estimated for each class. Option C, at a given point on the decision boundary, the class condition density correspond to both classes must be equal. At a given point on the decision boundary, the class condition density of to both classes may or may not be equal. So, kindly guess this. I want everyone to guess this. Okay, so your correct option will be A and D. Okay, A is very clear. It is assumed that class condition density of each class is a Gaussian. E is very clear. I have told you that Gaussian, whenever we are doing LDA, we are taking the assumption that covariance matrix of all these groups are equal. Okay, but here it has been tell a different covariance matrix estimated for each class. Class means group, same thing. So what we assume in LDA that covariance matrix for all this classes equal. So this is a false option. Now we have to see our things for the C and D option. So C and D option, at a given point on the decision boundary, the class conditional probability density to both classes must be equal. So they are talking about fkx and flx. So if we have two class k and l, so they are telling that fkx will be equal to flx. So that is not true, right? whenever we are talking about this decision boundary, I have already told you that logic function will be equal to 0. So we have equated it with equal to 0. Now fkx will be equal to f1x only when pi k will be equal to pi l. That is the equal, if we have equal number of sample pi k as well as pi l, in that case only fkx will be equal to flx. Okay, otherwise if pi k is not equal to pi l, then fkx will not be equal to flx. So option C is not correct. Okay, must be equal, it is written, must be equal, it is not correct. Okay, now option D, at a given this is the class conditional probability density corresponding to both classes may or may not be equal. Yeah, it is may or may not be equal. May be equal when pi k equal to pi l, will not be equal when pi k is not equal to pi l. So option A is correct, option D is correct. Okay, so is this clear?
Yes.
Okay, I think this should be clear to all of you. This is pure maths, maths in the second part, and for A and B, this is totally assumptions. Okay? Okay. Now consider the following two datasets, two LDA models trained respectively on this dataset. We have two dataset A 100 samples of class 0, means we have two classes 0 and 1. Okay, so in dataset A we have 100 sample for class 0 and 50 samples for class 1. In dataset B we have 100 sample of class 0 and 100 sample of class 1. How it is created? It is created by repeating twice the class 1 samples from dataset A. Okay, so what does this mean? This means that the mean of both this dataset A and dataset the mean of classes is class 0 as well as class 1, if we compare in dataset A and B, that means if we compare mean of class 0 with in dataset A and mean of class 0 in dataset B, that is equal, because we have 100 sample of class 0 as well as 100 sample of samples of class 0. Okay, now what about here, sample of class 50 sample of class 1, but here we have 100 sample of class 1. But how it is created? It is created by repeating twice the 50 sample of class 1 again. That means for this class also the mean is equal, but we will not tell the same about number of data points here, that is 150, that here that is 200 data points. Okay, this is clear. Now the classifier is defined as the following terms. Okay, wtx plus b, this is a straight line equation. So what they have done, they have converted the LDA into a straight line equation, and they have told that if the result of this straight line equation is less than 0, this is class 0, and if the result of the straight line equation is greater than 0, we will term it as class 1. And now they are asking the question, which of the given statement is true. Option A, the learned decision boundary will be same for both models. Okay. Option B, the two models will have same slope but different intercepts. C, the two model will have different slopes but same intercept. D, the two models may have different slope, different intercept. So this is the equation of discriminant of our LDA model. Okay, so this is the equation of the decision boundary or discriminant of the LDA model. Okay, this is the equation. Now we have to compare this equation with this straight line equation. Now the first term, okay, this first term, here also we have input and here also we have input, and this we can consider as slope. Okay, now what about this intercept? These two terms can be considered as intercept. So again I am repeating, if we compare this equation with this equation, here we have input, here we have input. The something with input is your slope. Okay, so this term, we can say this term, uh, this term is your yeah, this term is your slope, and this two term will combine together and form the intercept b. Now the learn now we have four options. The learned decision boundary will be same for both model. Is it same for both models? Now if we see the this term, okay, if we see the slope term, we can say mean is equal. How the mean is equal? You can see both for the k class, both for k class, or both for k, let's say k is your 0 class and l is your 1 class. Okay, so both for this classes you can see the mean is equal. How the mean is equal? Here also we have 100 sample for class k, and here 100 sample for class k, and here we have 50 samples of class 1, but here we have 100 sample of class 1, but mean is equal because 100 sample is found by repeating the 50 samples twice. That means mean of the k classes in dataset A as well as dataset B, as well as mean of L class in dataset A as well as uh, uh, dataset B will be the two model will have yeah, the learned decision boundary will be same for both the models. So data set means we are talking about models. Okay, so you can see in these two models the mean is same, right? Mean is same for these two models, model 1 as well as model 2. You can see the mean is same, but what about mean is same? As the mean is same, this term will be same for both the for both the model. This term will be same. But what about intercept? The intercept also contains this pi k value, and this pi k value will depend on the sample size for each class. Okay, and here we can clearly see that sample size is not equal in dataset 1 as well as in dataset 2. Okay, so that is why slope is equal but intercept value is not equal, because here also we are talking about intercept. So intercept value is not equal, but slope is same for both the models. So option B is your right answer. So is this clear?
Yes, sir.
So can you please explain once, please, sir?
Yeah, can you please repeat?
Yeah, can you please explain the second point? That is, the two models will have the same slope but different intercepts.
Okay, let me raise it.
So that pi k, how does it have? How does it depend on the class size?
Yeah, pi k will depend on the sample size of each class. Okay, pi k means yeah, mu k means mean. Okay, pi k means it is related to variance. Okay, so variance, it always depend on the scatter of the data points, so will always depend on the number of data points. Okay, or the sample size. Okay, so yeah, so let me explain you again. Yeah, so we know this discriminant equation for LDA. Okay, this is a discriminant equation for a LDA, and here we are comparing it with the straight line equation. This in this straight line equation we can see this x is your input, right? And wt is always a slope. This is the slope. Okay, this is the slope, and this is the intercept part. This is the intercept part. Now we will be comparing this equation with this equation. So this equation where there is input, the term related with it is your slope. So here this is the slope, and the remaining thing, this is the intercept. Okay, this is the input, this is the slope, and this is the intercept. Okay, now the first point, the learned decision boundary will be same for both model, and we have B, C and D option. The two model will have same slope, different intercept. Two model will have different slope, different intercept. Two model may have different slope and different intercept. So these are the four option given. Okay, so two model means one model will be formed by dataset 1 and second model will be formed by dataset 2. Okay, now whenever we are okay, some disturbance is coming. Okay, okay, yeah, so what I was telling is, disturbance coming. Okay. Slopes. So this is the slope terms will only dependent on mean of the two classes. Okay. This slope term will only depend on mean of the two classes. This two classes mean will be same. Why mean is same? Because here also 100 sample of class 0 and here 100 sample of class 0. Here 50 sample of class 1, here 100 sample of class 1. But the thing is, this 100 sample is created by repeating twice the class 1 sample from dataset A. Means 100 sample is created by repeating 50 plus 50 sample. This 50 sample have mean mu1 and this 50 sample have mean mu1. That means the for 100 sample the mean will be mu1 only. Okay, so mean is equal for both. If we compare both the models, this mean is equal. Okay, as this mean is equal, this slope term will be equal for both these models. Okay, but what about intercept? Intercept will be dependent on pi k and pi l. That means intercept will be dependent on variance. That means intercept will be dependent on sample size. Variance is dependent on sample size, so intercept will be dependent on sample size also. So what is happening in dataset A? Dataset A, we have 100 sample of class 0 and 50 sample of class 1. But here in dataset 2 we have 100 sample of class 0 and 100 sample of class 100 sample of and 100 sample of class 1. Okay, that means here we have 150 sample, here we have 200. Okay, 200 sample. Okay, so 100 sample of here we have 150 samples, here we have 200 samples. That means this intercept value, intercept term, as intercept terms contains pi k and pi l, this intercept term will differ for both the model, but the slope terms will remain equal. So option B is your correct answer. Okay.
Okay. Okay.
Okay.
There is this X transpose. It doesn't matter, is it? Here we are having this X transpose, right?
Yeah,
In our LDA.
X transpose, that is only for writing the matrix. Okay, so don't
Okay. Okay.
bother about
Okay.
that. X is for input.
Okay.
Here X is for input, here X is for input. That is the thing. Okay.
Okay. Okay. Okay.
Okay, so let's talk about this. Which of the following statement about LDA is are true? One or more choices may be correct. Okay, option A, it minimizes the between class variance relative to within class variance. B, it maximizes the between class variance relative to within class variance. C, both A and B. D, neither A nor B. So any guesses for this? This also I have explained in your theory part. Okay, B. Any other guesses? Not A, right? Yeah. So let's move to this. So I have told you this is very this is variance between the classes. Your numerator is variance between the classes, your denominator is variance within the classes. So our variance within the classes should be minimum, our variance between the classes should be maximum, so that our data points are well separated in our LDA line. Okay, that is the concept. So here same thing has been asked in question number 9. It minimizes the between class variance. So between class variance, our Fisher is between class variance. Okay, between, let's say between
That
B
is
and within
mean.
B. So within B, so this should be large as possible, and this should be small as possible. Okay, so it minimizes the between class variance relative to within class variance, so that is wrong. because between class variance we have to maximize. So option B is correct. It maximizes the between class variance related to within class variance. So option B is your correct answer. Okay, C. Okay, again there is some problem. C is wrong. Yeah, option B is only correct here. Okay, option B is only correct here. Is this clear?
Yeah,
It is
yes.
clear,
Few
right?
minutes.
Yes.
Okay. So, which of the following statement regarding logistic regression (NLD) is a true for binary classification problem? Option A: for any classification dataset, both algorithm learn the same decision boundary. Option B: adding a few outlier to the data is likely to cause a larger chance in decision boundary of LDA compared to logistic regression. Option C: adding a few outliers to the dataset is likely to cause a similar change in decision boundary of both the classifier. Option D: if within class distribution deviates significantly from the Gaussian distribution, logistic regression is likely to perform better than LDA. So, any guesses for this? You can guess this also, I think. Okay, someone is telling B. Okay, okay. So the correct answer is B as well as D. Okay. Always remember that in Gaussian distribution, Gaussian distribution, you say the error terms. Okay, in whenever we are doing error in this logistic regression, we are taking out the maximum likelihood. And LDA, whenever we are computing the error. Whenever we are computing the error or finding the decision boundary of LDA, there we are using the Bayesian classification. Okay, so since LDA assumes that underlying intra-class distribution are Gaussian, outliers have a greater effect on LDA compared to logistic regression. Okay, logistic regression also by equation you can understand it. Logistic regression does not consider any pi k terms. Okay, it does not consider any pi k terms, but your LDA consider your pi k terms. And D is also like that. LDA will not perform well if the data does not satisfy the assumption of the model. On the other hand, logistic regression does not make any assumption about the data distribution. So this is explaining about A point. Okay, now D point: if within class distribution, okay, that means the below thing S square. Okay, if within class distribution deviates significantly for Gaussian distribution, logistic regression is likely to perform better than LDA. Again, whenever we are talking about variance of the data, always remember that your logistic regression will perform well than your Gaussian distribution. Okay, because Gaussian distribution also takes the pi k terms. Okay, but your logistic regression does not consider those terms. Okay, so option B is correct, also option D is correct. Okay, so is this clear? B as well as C. No, C is not correct. Adding a few outlier on the dataset is likely to cause similar change. No, similar change is not correct, because logistic regression, it always have lesser change. Okay, what the decision boundary.
Can you please show me question number 9 if you don't mind, please, for a few minutes?
Yeah, this is the question number 9. This slide I will also provide in that folder. Okay.
Yeah, sure. Thanks a lot, sir. That's
Okay. Okay. So that's all for today's lecture. Okay. So any major doubt in any portion? Can clarify?
So, can you tell about the projection vector for LDA, like the direction of weights? There was a question.
Okay, direction of
Finding
weights.
direction of weights based on
No, I have not
the
covered in the
between class and in. Okay.
that portion. I have not covered. You can probably cover it from lecture notes only. Okay. weights, that means okay. Weights, that means okay. Direction of weights, okay. You can
Yeah, that metrics thing, it's not very clear from the lecture.
okay.
That's
So
why
next class I
how
will
they are doing
yeah,
the.
I will be
Okay,
considering that portion in the slides. Okay.
okay, okay.
So any other major doubt? Okay, no major doubts are there. So by that I'm ending the session for today. Thank you everyone for joining. We will meet on next Monday. Okay.
Thanks, sir.
Thank you, sir.
Okay. This yeah, the slides as well as the YouTube video for today's discussion will be available on that live section or live session, right? Live session at the bottom of your weeks. Okay. From there you can get that YouTube link also for today's class. Okay.
One more doubt, if you
Yeah, yeah.
have time.
Yes, please.
Yeah, so that for the initial Bayes rule theorem when he was applying, right, f of x into pi I divided by summation of f of x into pi L. That that there, what does pi represent when that Bayes rule was being applied?
Okay. These.
No, in the lecture in the LDA starting, initially he was applying Bayes rule to uh,
This
find the
pi.
probability. Yeah,
This pi.
yeah, that pi. Yeah, yes.
Yeah, this is prior probability of class K.
Uh, but you are also referring to that as
Yeah,
variance, right? So that was confusing.
yeah, yeah,
Y-
yeah. Actually, this prior probability depends on the variance also. Okay, that depends
Okay,
on sample size as well as variance. Okay, so you
okay,
can take that concept of variance here.
okay.
Okay, okay, okay. Bye everyone. Okay, yeah. Someone is asking, sir, please pass the drive link for the YouTube, please. Okay, drive link for the YouTube. There's no drive link for the YouTube. YouTube, you will get link for each week. Okay, there's a drive link for a folder. In that folder, you will get this slides. Okay, is it clear, Lakshmi? Hello, is it clear, Lakshmi? Okay, okay, okay. So bye, everyone.